The Great Attractor isn't, it aggregates. To understand why a direction started acting like a rule, we have to stare into the worst window on the sky. The zone of avoidance sounds dramatic, but it's just honesty. The plane of our own galaxy throws up dust and stars that block our sightlines. Right behind that glare sits the putative Great Attractor. You can't simply take a deep exposure and call it solved. So astronomers did something sneakier. If you can't see mass, you can still feel motion. They inferred the lay of the land from the way galaxies swim. Velocity fields first, light maps second. That's where velocity fields became the main character. Take thousands of distance estimates, subtract the smooth Hubble expansion, and you're left with peculiar velocities, the deviations that tell you how galaxies fall through the local gravitational landscape. Feed those into reconstructions that tame noise but respect physics, Wiener filtering, constrained realizations, and a picture emerges. Not a single mountain, but a basin. Converging flows spread over a swath of sky, bending around obscured structure yet maintaining a stubborn net vector. Meanwhile, teams kept adding up the ledger of known mass. The Centaurus and Norma clusters live in the masked region. They matter. Extend the radius and you hit the Shapley concentration, a heavyweight that absolutely tugs. But here's the rub. When you fold those into the calculations, the flows don't close. The residual bulk flow remains. It's there in cautious phrasing, may indicate, requires further mapping, but it's there across methods. Gravity is doing what gravity does, yet the field acts like something broader than a single attractor is setting the direction. Get this, when you visualize the flow lines, they don't spiral neatly into one point like water into a drain. They contour around knots, skirt walls, and still trend the same way, as if the entire region is sloped. That slope isn't a dot on the map, it's a behavior. It's the difference between chasing an object and recognizing a basin of attraction dynamic, where the combined pull of many masses and the push from underdensities together guide traffic. Here's where the language trips us up. Great Attractor implies a monster hiding in the weeds, but the data keep demoting that image. You see gravitational dipoles pull here, push there, manifesting as coherent flows over vast scales. You see lines that curve around the zone of avoidance, respect what we can't yet catalog, and still keep the same net heading. Every time surveys punch a deeper hole through the dust, more structure appears, but the vector doesn't swing wildly. If a single body owned the story, new discoveries would torque the arrows. Instead, the basin holds. While that was happening in redshift space, something else was happening in how we talk about where here is. The shift to basins means boundaries aren't where density peaks end. They're where streamlines fork. That's a different kind of map. It says your fate is written less by a single summit than by the shape of the valley. In that frame, the Great Attractor isn't a destination. It's part of a gradient, a region where the combined field aggregates motion into a preferred direction. But there was one problem, and it wouldn't go away. Shapley helps, but it doesn't close the books. You can bias correct the galaxy surveys, model the dust, account for selection effects in the zone of avoidance, and the residuals still hum. The flow stays too coherent, too straight for too long. That coherence is the tell. It suggests we're not just summing masses, we're seeing a large-scale rule play out. The rule might be as simple as follow the easiest path, but easy here doesn't necessarily mean deepest potential well. Now flip the perspective. Unknown to many when researchers trace the same velocity field backward, asking, from where would you have to be repelled to get this bulk motion? A different culprit appeared on the opposite side, a deep underdensity. In the reconstructions, it registers like a repeller, not magic, just the consequence of having less matter. Expansion runs less hindered there, and the flow lines tilt away. Pair that with the basin we call an attractor, and you get lanes, attractor, repeller partners shaping a corridor. This is the moment everything changed in how the community framed the mystery. The attractor wasn't a single throne. It aggregated influence across a masked, messy region and beyond. The repeller wasn't a hand pushing. It was empty space pulling less, letting the universe's expansion act like a tailwind. Put them together, and you understand why the vectors keep their heading even as new masses are logged. The field is writing a rule over a wide area. A microstory lands it. An analyst overlays new HI detections peeking through the dust. The contours shift slightly, more mass here, a tweak there, but the streamline he's been tracking barely budges. He laughs, not because the problem's solved, but because the behavior's clearer. "We're chasing a slope," he mutters, "not a summit." So if not a mass, what sets the vector? You can keep extending the map and hope the ledger balances at the next survey depth. Or you can ask whether the rule arises when a domain acts like a system with limits, where flows prefer configurations that conserve something scarcer than matter. To understand the pull, we need to test the ledger, and then decide what to do when the ledger won't balance. The missing ledger problem, where the mass should be. To understand the slope, we have to open the books. Cosmology runs on ledgers, densities, distances, velocities, balanced by gravity's math. When you see a flow, you ask what mass makes it. When you see a lot of flow, you ask where the extra mass hides. Simple rule. Except here, the math keeps coming up modestly short. Start with what we can count. Luminous matter, stars, gas, hot plasma in clusters gets mapped in light. Add galaxy redshift surveys to trace overdensities. Correct for bias. Galaxies are not perfect tracers of dark matter, so you calibrate how light sits inside halos. Then fold in weak lensing, X-ray cluster masses, Sunyaev, Zeldovich signals. On the largest scales, impose the cosmic microwave background's constraints. The early universe sets the budget of matter and the shape of the primordial spectrum. You build a reconstruction of where gravity should be strongest, where it should be weakest, and how far that influence should reach. Meanwhile, you build the other side of the ledger, motion. Peculiar velocity surveys pull distances from standard candles and rulers. Type Ia supernovae, Tully, Fisher for spirals, fundamental plane for ellipticals. Subtract the smooth Hubble expansion, and you get the sideways tug, the deviation from pure recession. Feed those into velocity field reconstructions that use methods tuned to the norms. Wiener filters to recover large-scale modes without chasing every small bump. What drops out are streamlines, bulk flows, shears, the language of motion. Now compare the ledgers. On the mass side, the reconstructions deliver. You get a lumpy universe, clusters where they should be, superclusters like Shapley flexing muscle at the distances we expect. On the motion side, the reconstructions overdeliver, coherent, peculiar velocities that keep a heading longer than the mapped mass says they should. You can feel the caution in the phrasing across papers. Residual bulk flow remains. It's the sentence you write when you've subtracted everything you trust, and the number still won't go to zero. What if we just missed a lot of matter? Fair question. The zone of avoidance eats photons. Teams have pushed 21-centimeter HI surveys through the dust, stacked infrared catalogs, modeled selection functions that fade galaxies out near the Milky Way's plane. Each pass recovers structure. Norma brightens, Centaurus grows spines, a Vela concentration takes shape. The vector jiggles. It doesn't break. The basin keeps its tilt. If a single hidden monster were responsible, the direction would pivot as new mass was logged. Instead, the velocity field behaves like a rule written over a wide area. Another suspect, bias in how galaxies trace mass. Change the bias factor and you do change the inferred gravity field. People have. Independent groups have. They tune the bias, widen the error bars, swap priors. The same melody returns flows that are too straight, too extended. Push farther, assemble deeper redshift slices, reach out into volumes where Shapley lives. Shapley helps. It can't close the books. You still need a push, or rather, you need less pull in another direction. Here's a detail that matters. The flow field isn't just a dip toward one side. It often plots as a dipole, attractor here, repeller there. When you look at the shear and divergence of the velocity field, that repeller shows up opposite the Great Attractor direction in some reconstructions, at a distant scale that matches a known underdensity. It's not anti-gravity. It's gravity's absence letting expansion run easier, tilting the trajectories away. When you include both sides of the dipole, you explain why the vector holds steady while masses are added. You're not chasing a point, you're navigating a gradient. But the larger problem persists even after that insight. When you seed the reconstructions with the best mass maps we have, the amplitude and coherence of the bulk flows still brush the high end of expectations from standard lambdictum on the scales probed by those catalogs. Not break them, strain them. Enough to keep language cautious and nights long. Enough to keep the residual alive across datasets like cosmic flows and its updates. You can feel the community holding two lines. Gravity explains the web's shape. Yet, around Laniakea, the preference for one long corridor seems stronger than the sums predict. A micro-story captures the tone. An author revises a draft after peer review. Reviewer 2 asks for another bias correction and an extended mock catalog test. They add both. The main figure barely changes. The new caption gains one clause. While systematics cannot be excluded, the coherence of the inferred flow persists across reconstructions. That's scientist for. We tried to kill it, it's still breathing. So what do you do when the mass ledger refuses to close but the motion ledger is stubborn? You can always say, deeper maps will fix it, and maybe they will. Or you can admit a second possibility. The rule we're watching might not be only about matter, not new forces, no need to rip out general relativity, but limits. Hard constraints that tell a region how much state it can carry, how much complexity it can maintain before the cheaper path is to streamline the flow. If that sounds abstract, hang on. Physics already has ceilings that act like this, bounds on information, budgets that couple energy and bits. When gravity can't close the gap, check the system's limits. Hard ceilings in physics, information before matter. To see what a rule might be, we have to leave maps and follow limits, not walls, ceilings. Physics is full of them. Start with the strangest, black holes. Throw stuff in and you'd think the information about that stuff vanishes. Except thermodynamics hates that. Hawking radiation says black holes have temperature. Bekenstein argued they have entropy, and that entropy doesn't scale with volume like a pantry. It scales with area like a door, the seed of the holographic viewpoint. Get this, the maximum information you can pack into a region isn't set by how much room you think you have inside, it's set by the surface. That's the Bekenstein Bound. In Planck units, the count goes like area, not volume. Apply that logic to the observable universe and you land on a huge but finite number, on the order of 10^123 bits. Not infinite, not arbitrary, a ceiling. Why does that matter here? Because a bound on information isn't philosophy, it's bookkeeping. Entropy is just a way of counting states. If a region can only hold so many distinct arrangements before it forces a new phase, collapse, radiation, or some other release, then complexity can't grow without paying a cost. That cost shows up as energy, temperature, or a change in configuration. There's another rule that ties bits to heat in a way that's almost annoyingly concrete. Landauer's principle. Erase one bit of information in a system at temperature T, and you must dissipate at least kT ln2 of energy as heat. It's not optional. It's how the first law keeps score when you compress state. Engineers meet this limit at nanoscale. Black hole thermodynamics is consistent with this bookkeeping at horizons. Information has a price. Now fold these two together. A ceiling on how many bits fit in a region, and a minimum energy cost when you erase or compress them. Suddenly, the idea of a budgeted domain stops being metaphor. If the physics of a region is already near its information saturation, because of the structures, interactions, and degrees of freedom sloshing around, then further growth of detail can't be free. You can compress, simplify the configuration, export, move degrees of freedom out along a gradient, or erase, pay, and heat. Here's where the story brushes Laniakea without forcing anything exotic. Imagine basins of attraction as compute domains with finite throughput. They're not computers in the laptop sense, but their microphysics moves bits around all the same. Particle states, field configurations, coarse-grained information about who's where and doing what. Growth of structure is like adding detail to a file. At first, no problem. Later, the margins pinch. The bound looms. If that's too abstract, anchor it at a horizon. A black hole's entropy goes up with area, and when it evaporates, it releases the bookkeeping as radiation. The system pays to erase its interior bits. In our larger, expanding universe, we don't have a literal wall around Laniakea, but we do have effective boundaries, separatrices in the velocity field, and a cosmological background that sets clocks and frames. Within those, there's still a budget, limited capacity for distinct, stable configurations before the cheaper path is to push complexity outward or smooth it. Here's the move. When gravity alone can't close a flow ledger, ask if an information ceiling is guiding preferences. We're not changing Einstein. We're asking what happens when the allowed microstates get tight. A domain under pressure will seek minimal description pathways. That's algorithm speak for choose the simple route. In cosmology, the simple route tends to be under dense corridors, fewer interactions, lower potential complexity, easier streaming. Voids grow, filaments sharpen, and flows align along lanes that minimize representational cost, an effective preference layered on standard dynamics. What would an overflow look like? Not a flashing error, but a systematic bias, anisotropic compression in dense regions and preferential export along low-density vectors. It would feel like a rule because it's not a single mass dictating traffic. It's the whole domain relaxing into configurations that fit the ceiling. And crucially, any erasure, any coarse graining of detail wouldn't be free. Landauer says it comes with heat. On cosmic scales, that heat could be subtle, a bookkeeping adjustment in energy distribution rather than a bonfire. But it should leave signatures, temperature imprints, entropy shifts, timing of structure formation that tilts toward later assembly where budgets are tight. Meanwhile, something else is happening globally. The holographic hint that nature tracks information at boundaries means our intuitions about stuffing more inside can mislead us. You don't get infinite headroom by carving more shelves in the same room. Past a point, you reinforce the door or you start sending boxes out. In the cosmic web, sending boxes out looks like streaming galaxies through void corridors and tapering growth where the basin's ledger runs lean. Now remember the language from the flow mappers. Residual bulk flow remains. The vector holds, the lanes stay coherent, even as more masses are added to the catalog. That's not proof of a ceiling, but it's exactly the flavor of a preference born from constraint rather than a single source. If the system is near its informational headroom, the render changes shape. You keep the big features, you simplify the rest, and you route traffic where it's cheapest to keep track. Hold that thought. If the code is stressed, the render changes shape. Next, we'll ask whether Laniakea itself looks like a compute-bounded basin, and what cheap lanes look like when galaxies have to pick them. Laniakea as a compute-bounded basin. So let's treat Laniakea the way the velocity mappers taught us to, not as a pile of stuff, but as a working domain, a basin with inputs and outputs. In that frame, basins of attraction aren't just where gravity wins, they're where motion gets organized. Now add one twist from our ceiling idea. Each basin has a finite throughput for the amount of state it can stably store as distinct configurations. Not a literal hard drive, but an effective budget written by microphysics and the background expansion. How do you draw the walls of such a domain? You don't start with density, you start with streamlines. Seed a point near us and follow the peculiar velocity field forward. The path runs along the local sheet, nods at Virgo, then keeps surfing the same large-scale lean we've been watching since the cold open. Seed a point just outside the domain and watch the line peel away, slip into a neighboring watershed and never come back. That fork, the separatrix, is your boundary. It isn't a cliff. It's a choice architecture embedded in the flow. Now plug in the ceiling. If the basin's informational headroom is pinched, flows will prefer minimal description pathways, routes that keep interactions sparse and bookkeeping simple. In the cosmic web, those routes run through underdense corridors, fewer halos to navigate, fewer mergers to track, lower gravitational complexity per unit path length. Gravity sets the terrain, constraint sets the preferred lanes. Here's where Shapley's odd roll starts to make sense without turning it into a final destination. On the maps, Shapley looks like a big cache, plenty of mass, real pull, but the streamlines we care about don't stop there. They curve, acknowledge the weight, and continue along the corridor. If you've ever worked with a machine that's memory-bound, you know the feel. A fast cache helps, but if the bus is saturated, throughput caps your performance. In Laniakea, the bus is the low-density highway. The flow optimizes for that. What would that look like along our path? Filaments sharpen where they have to carry load. Voids adjacent to those filaments relax and expand, opening lanes. The peculiar velocities we measure should tilt to those corridors, even when a nearby overdensity tempts a detour. And that's what the reconstructions quietly show. Streamlines that skirt knots, skim walls, and rejoin the same outbound vectors. It's not that the dense nodes don't matter. It's that the domain acts like a traffic system trying to avoid expensive intersections. Meanwhile, human cartographers face a headache. Labels love objects. Supercluster wants a boundary you can circle with a marker. But in a compute-bounded view, the border is behavioral. It's where the flow splits based on cost. That's why Laniakea's definition by velocity lines felt so fresh when it landed. It matched how the system actually routes its state. The irony is that labels always lag the process. By the time we name a feature, the lane has already adjusted to new balances in pressure and pull. We need one more uncomfortable piece. The zone of avoidance isn't causing any of this, but it's a perfect metaphor for how constraints hide in plain sight. You clear a bit of dust with a new HI survey, add more galaxies to the ledger, and the corridor still shows up. The anomaly survives better maps. That's exactly the behavior you expect from a rule that isn't about a single hidden lump. It's about the system's preference. Keep the lane open, keep complexity exportable, keep the cost down. Now, does this story overrule gravity? No. It reframes priorities inside the same laws. General relativity sets the potentials and the expansion. The matter distribution sculpts wells and hills. On top of that, the finite capacity for distinct, long-lived configurations in a given domain nudges the flow towards simpler routes. When you're near a ceiling, small energy savings matter. Landauer reminds us that compressing state isn't free. On large scales, that pressure favors pathways with fewer erasures and less turbulent mixing. A micro-story to ground the abstraction. Picture a galaxy group, a modest dozen halos deep, approaching a junction where two filaments meet. One path threads past a cluster, rich with satellites and hot gas. The other skirts a void's lip, quieter by far. In pure potential terms, the cluster tugs harder. In the lived field, the group's peculiar velocity tilts to the void lane, not because the cluster vanished, but because the corridor asks less of the system to keep track of. The group chooses the cheaper lane without choosing anything at all. While that was happening in the data, another realization hardened. The outbound heading from Laniakea isn't just any line. It aligns with known underdense regions that act like the universe's slipstreams. That alignment is the tell. You can't fake it by sprinkling more dark matter behind a dust band. The preferred route goes where interactions are few. And once you see it, the basin stops being a box on a diagram and turns into a live network under soft budget pressure. So here's the question that follows if Laniakea is compute-bounded. Where does the excess go when the basin saturates? If compression sharpens filaments and export prefers void-facing lanes, then there should be destinations, places that accept state without pushing back. In the velocity field, those look like persistent corridors leading away from the basin. In the sky, they look like emptiness doing work, which means our next stop isn't a cluster at all. It's the quiet architecture that makes export possible, the voids. The data drain hypothesis.